This is Jack Jackson, and we're going to be looking today at inferences about variances or variability from one sample. So what we're doing here is we're taking one sample and we're finding the variance of that sample, or we may be finding the standard deviation. Of course, remember the variance is just the square of the standard deviation, or the standard deviation is the square root of the variance. So knowing one basically tells us the other. So we're going to use this variance from a sample variance, and from this one sample, and that sample variance we're going to compare basically to some known variance, and we're going to compute a statistic called a chi-square statistic. Now remember that if you take a bunch of samples and you compute a statistic each sample, and then you look at the distribution of those statistics, that is what we call a sampling distribution. And of course that's been the whole basis of doing our inferential statistics. Particularly we've looked at this a lot when we were doing the distribution of sample means. X bars have a distribution. Of course we know that's more likely to be closer to normal than the original distribution was, unless they're both normal to begin with. In a similar manner, we can take other statistics and they have sampling distributions as well. So in particular, we're going to look at today a sample variance as square of a sample. If we do that over and over and over again, it has a distribution as well, has a sampling distribution. Now, if we have a special case where the underlying population of individual values is a normal distribution, or is distributed normally, then it turns out we know a lot about the sampling distribution of S squared. Now we're going to standardize this somewhat like we did z-scores. Now remember, in z-scores what we did is we sort of took things from any normal distribution and then sort of scaled it back to a standard normal with mean 0 and standard deviation 1. It's not the same way we're going to do it here, but it's a similar concept. And so we're going to produce what's called a chi-square statistic. And what you do is you take your sample variance, your S square, we're going to divide it by the population variance, sigma square, and we're going to multiply by what's called the degrees of freedom, n minus 1, where n is the sample size. And so this little formula here computes this chi-square distribution. So basically we're scaling it back by essentially just dividing it by the population standard deviation, along with this other factor of n minus 1. So this test statistic, chi-square, is called a chi-square distribution. And this looks kind of like an X here. This is actually a Greek letter, chi, which we spell out C-H-I, but we pronounce it chi. And this is used for this particular distribution, chi-square. The square basically is used because of the S square and the sigma square. So chi-square distribution. Okay, so the distribution of test statistic follows a known distribution called the chi-square distribution with n minus 1 degrees of freedom. Now, if you remember back when we studied t-distributions, there was a different t-distribution for every different degree of freedom. And just like the t-distribution, the degrees of freedom will be 1 less than the sample size. N minus 1 is degrees of freedom. And so, like the t-distribution, every time we have a different degree of freedom, we'll have a slightly different shape for this chi-square distribution. They're pretty similar in some respects, but there are a little bit of differences. Now remember, when you look at this, just look at the things that are making up this distribution. You've got S square and sigma square, which are both positive. N minus 1 will be positive. So the chi-square distribution always produces a positive value. So if we're dealing with a chi-square PDF, it will only have positive values. So if you want to think of it for negative values, it's just 0 from negative infinity to 0. You can do that if you want, or you can just say it's only defined for positive values and 0, but not defined for negative values. So basically we're just going to say it's only defined from 0 to infinity. And of course outputs are always positive as well, so for PDFs. So we're only looking at a first quadrant graph. Now the formula for this has this kind of a format: some constant, which depends on n, which I'm going to call C of n, and then x to the power n minus 3 over 2 times e to the power negative x over 2. That's the basic formula. C over n is kind of a complicated formula, but it depends on n, but it is a constant that doesn't depend on x. Totally irrelevant for what we're doing about that formula. You don't need to know that formula. Just it's there for reference. But we do have a different formula, a different one of these formulas for each different value of n. Now here's what some of the PDFs look like for this chi-square distribution. Okay, now degrees of freedom are 1, which means we have a sample size of 2, is actually very different than the others. It's basically starts up here and comes down, concave up. But all the rest of them, degree of freedom 2, 3, 4, 5, and so forth, so sample size of 3 or bigger, they start at 0, 0, goes up, maxes out, and comes down. So this dotted one right here, if you can see where my cursor is moving, that's going up and down. That's degrees of freedom 2. This black one is 1. Then the green one going up and back down is 3 degrees of freedom. And this blue one is 4 degrees of freedom, 5, 6, 7, 8, and so forth. So I've got it graphed through, actually from 1 to 10 I've got graphed here. These graphs come from Minitab. So statistical packages like Minitab, SPSS, and so forth, they can graph these things pretty easily. So let's look at a couple of examples, actually 3 examples here, and look at the characteristics of the chi-square distribution. They all start right here at 0, 0. This is for degrees of freedom 5, 10, and 15, so that means the samples of size 6, 11, and 16. And notice it goes up, maxes out, comes back down, but it comes back down more gradually, and so all of these are skewed to the right. The smaller the degrees of freedom, the more pronounced that skewing is, and the more skewness that we have. And so the larger the sample size, the more it becomes like a symmetric, but it's still skewed a bit. So the red one's a little less skewed than the black one, and this green one here at 15 degrees of freedom is starting to be closer to symmetric, but you can still definitely see that it's skewed there to the right. Now, this was using a statistical package. It turns out that we have built-in chi-square PDF and CDF built in. And just like the t-distribution, there's one for every degree of freedom, but if we specify the degree of freedom, we can graph PDFs and CDFs. So here's what you do on a TI-84. You go to Distribution, okay, second VARS, Distribution, and the PDF is number 7 and the CDF is number 8. So right now we're just going to graph the PDF. So we choose number 7, chi-square PDF. First we go to y equals, of course. So go to y equals, up here at y1, get on there, then go to Distribution, second variables, click on number 7, chi-square PDF. Then we put in our variable x, because we want it to be at a variable place, be a function of x, and then we put our degrees of freedom. For this example, I'm using degrees of freedom is 5, which is a sample size 6. So this graph is the same as the black graph here, maybe a little bit different scale, but here it is. This one's 5 degrees of freedom, and here's the graph in our calculator. Okay, well, as with most things, you're going to have to figure out a reasonable window to use. We really could have started at 0 on x and y, but I want to leave a little dead space here because later on I might want to do some calculations or something that show up down here. Okay, and it turns out, we'll see a little bit later, that if you go out about 2.5 times the degrees of freedom, that works out pretty well. Let's see if I did that here. 2.5 times this would be about 12, 13. I actually went out further than that. I went out 20, so I went out a little bit further than I needed to go, because we're already down pretty close to the axis when we're about 13. And then you have to kind of figure out how high to make it. A little trial and error there. I went up 0.3. Could have gone down. Could have come in a little bit smaller than that, actually. A little smaller than 0.3 would probably been better. And I went enough negatives just to leave me some space there. But this is a pretty decent looking graph. We might tweak the window a little bit, but that looks good. So we can graph the PDF. So just like you can graph the PDF for a normal or a T distribution, you can do the same thing for a chi-square distribution. And you basically don't even have to know the formula for the actual normal or T or chi-square. All you really have to know is that it's just a chi-square PDF. It kind of tells you that. Okay, so we can of course use that to calculate probabilities, just like we can with any time we have a formula in our calculator for a PDF. And we can do it with our basically our area calculator in our calculator, which is Calc 7. This is this integral of f of x, the numerical integral. And remember, that's our area calculator. And if you're doing it from Calc 7, from the graphing menu, it'll shade and compute. And that's what I'm going to use here. So what if we want to find the probability that chi-square is less than 3? Again, we have 5 degrees of freedom. Okay? So again, our formula needs to be in chi-square PDF x, comma 5. First number is your x value, which is going to be a variable x. Second number is our degrees of freedom, which is 5. And we're going to go to Calc, second trace, and hit number 7, and get this. Choose it. It's going to ask us for a lower limit, which is 0, and an upper limit is 3. Of course, less than 3 is really just 0 to 3, because there's nothing less than 0 in this particular distribution. And it'll shade and calculate that area, which of course corresponds to that probability. Now, you should be having your calculator out and getting these same things on your calculator. If you've got a TI-84, the screenshot should look pretty much exactly like what you see here. If you've got a different calculator, see if you can get your calculator to do the same thing. Be sure that you get these screenshots before you move on. So if you need to, at any point in the video, you can pause, make sure that you're getting these things to come out of your calculator before you move on. Okay, let's go on now. Now, since we also have a chi-square CDF built in, we can graph that too. And we can use it to find probabilities, cumulative probabilities as well. So, again, go to your y equals. This time I want to graph both of these things together. So, I've done this without erasing my shade. In fact, I redid this on this new scale so that the shading would still be there. But I'm also going to graph the chi-square CDF. So number 2, y2, is chi-square CDF. Now remember, chi-square CDF is right below chi-square PDF. They're found under distributions. So second, calc, and I think one was 7, one was 8, but you can find them in the list there. So chi-square CDF, and the syntax is left bound, right bound, and degrees of freedom. So we want to go, if we want a cumulative CDF, we really want to graph the CDF, it's going from 0 up to x. It's usually negative infinity up to the x, but remember, there's nothing between negative infinity and 0 on this particular curve. It's only defined from 0 up. So really our left end is 0, not negative infinity. So 0 to x, and we want x to be a variable, so we'll graph the whole curve. And then our degrees of freedom, we have to specify that. And so that's our number 5 is our third number we put in there. Now, I needed to change my window a little bit. 0 to 20 is still okay here. Like I said before, probably even 13, 14, 15 would have been okay. And I kind of use my standard negative 0.2 to 1.1 that I use a lot of times for CDFs, for the y limits, and graph it. It takes a little while to do this. I've also put my cursor over here on this little symbol to the left of y2 and clicked inner once to make it thicker, so that the thick line is the CDF and the thinner, thick curve I should say, it's not a line, it's a curve, but it's not a line, and the thinner one is the PDF. Now I went back at this point, and after I got the graph, and went ahead and shaded this using the same steps that I did back here on the last one, but I did it on this so it would show up the shading. And then I went back and then showed you how you can find the same probability on the CDF, and you just do that with a trace. So I hit trace and hit 3, enter, and it gives me this coordinate of this point right here on the CDF, which is x is 3, y is 0.30001416. Okay, which should be the same y value that I got for the area on the other curve. So they should both be the same. The last digit's off. So one of those, these are using approximation techniques. So that's one of them is rounding off just slightly wrong. Of course, in a real world problem, we won't need to go out that far anyway. But these are supposed to be the same value. So let's go here, and we can also use the CDF to compute some inverse probabilities. Now remember, when we had the t distribution or the z distribution, the normal distribution, standard normal, there was an inverse t and an inverse z built into the calculator because we use those particular commands so often it's useful to have them. Unfortunately, there's not a built-in chi-square inverse or inverse chi-square that will allow us to put in a cumulative probability and output a chi-square or x value for the chi-square distribution. However, we've studied these before. We know how to do this. So, for example, if we were given the cumulative probability as 0.1, that is the probability to the left of c that chi-square is less than some constant c, again at 5 degrees of freedom, is 0.1, we can take our chi-square CDF, again the dark increasing curve here. We graph the y value of 0.1, which is, remember on this curve, y values are cumulative probabilities. The cumulative probability is 0.1, and so we just want to find that intersection, do calc intersection like we've done many times. Of course, y is 0.1, and that x value, 1.610308, that is the chi-square value c, x value on this graph, where it gives us that particular output. And so this is the x value, so that the area to the left under the PDF is the same as the y value on this curve, which is 0.1, which is our cumulative area, our cumulative probability. So, not too bad. We can use this method here. In general, if we've got a CDF, we can use this to find inverse probability. In other words, inverse probabilities, where we're given the probability and we want to find the input or x value. Alright, let's do a few more things and describe our distribution a little bit. Calculate the following measures of central tendency. This time we'll use a chi-squared with 20 degrees of freedom. Let's find the median, the mode, and the mean. See if you can do the median. Should be able to do this based on what we just did. Press pause now. Come back when you've done it. Okay. Well, computing the median is very much like computing the other, the last problem we did. Before we do that, let's get our graph in there. And I've put in some important things. I'm going to put in the chi-square PDF x 20. And remember, 20 was the degrees of freedom. That's what we got here. What is the sample size then? Well, it's one bigger, so it's 21 is the sample size. But what you put in is the degrees of freedom. Chi-square CDF goes from 0 to x, 20 degrees of freedom. And I'm also going to graph 0.5. Why do I need that? Well, remember, the median is the x value, in this case a chi-square value, that gives us a cumulative area of 0.5. So we want to find where y2 and y3 intersect, and that will be that x value will be the median. And the x-min should be 0 here. Can't see it there. It's behind that square or rectangle there. It's 0. If you go about 2.5 times the degrees of freedom, that's a good upper limit. And 2.5 times 20 is 50, so that's pretty good. Not a hard and fast rule there, just something close. And if I'm going to go from 0 to 50, I'll mark it off in 5s. And here's sort of my standard window for that I like to use for CDFs. So what I need to do is just graph the CDF in 0.5. In this case, the PDF down here is really not important. Calc intersect. Now, if you have all 3 of these curves graphed like I do here, you got to be careful that you select the correct 2 curves when you're doing the calc intersect. The first thing it's going to do is ask you for the 2 curves. Use your up and down arrows to move among the curves until you identify the correct 2 curves, and then make your guess pretty close to the point where they cross and have it calculate that intersection. Of course, y is 0.5, and x there is the median, 19.33749. Okay, if you haven't gotten this yet on your own, if you didn't do it before I did it, go ahead and stop now and get this before we move on. Okay, what about the mode? Well, the mode is the x value of the maximum point. Well, the calculator has a way to do a calculate a maximum. So we're just going to use that technique. So again, I've graphed the chi-square PDF from x, 20, which this is the PDF. So now I've gone back down to zoomed in a little bit. I'm still going from 0 to 50 on the x's, but I don't need to see the CDF, so I've toggled that one off, and I took away the 0.5. I don't need that anymore. I might need the CDF again, so I've just turned it off without deleting it. And we need to zoom in quite a bit. It turns out if you just go to 0.1, this is 0.1 on the top y, and I did negative 0.03 for the y min, and that actually makes a pretty good looking window. Then I just need, once I got that graphed and I can see the maximum here, I want to do a calc maximum. So that's second trace for calc. Choose out of your list, find maximum on that list, choose it. It's going to ask you for a left bound, so go somewhere over here on the left side, hit enter. Right arrow over here somewhere on the right side for a right bound, click enter. Move it close to the top here and click enter when it says guess, and then it's going to output this, and notice you get 18 for that maximum, and y is about 0.066. Okay, so we don't have to go too high. 0.06, I've got it at 0.1. I could have gone to 0.07, probably would have been okay. Put the max right up towards the top. Anything above this guy right here for this y max would work. So we found the mode and we found the median. What about the mean? Well, remember that the mean is, you should be able to figure this one out. We've done this before. The mean is the expected value of x, which is the integral, well, over everything, and in this case everything is 0 to infinity, of x times the PDF. Okay? And so in our calculator, this is using the newer operating systems here on the left. Lower limit 0. Not knowing what's a good approximation for infinity, I just put in something really big, say 1,000. And then notice what I put in for the formula. X times chi-square PDF of x20. Or we could have put in y2 or y1, wherever I had this. I had it in y1. So since I had it in y1, I could just say x times y1 if you want. And then at the end over here, there's a dx. So it's the same things here. In the older operating system, it looks like function integrate instead of the integral sign. The input's the same. All 4 numbers are going in the same place. Different places, but the same thing. X times chi-square PDF of x comma 20 is what you put in for the first number, comma x, that's the x of the dx part over here, comma 0, that's your lower bound down here on this version, and 1,000, that's my upper bound up here, which is what we're using for instead of infinity. And that turns out to be 20. So, look what we have. We have the mode is 18, the median is 19.337429, the mean is 20. Now, you may remember that the degrees of freedom was 20, and so the mean was the degrees of freedom, and the mode was 2 less than that. Now, I can't prove this without using some calculus, so you're going to have to trust me on this. But you could try this out on several different degrees of freedom and find the mean and the mode, and every time you're going to find out that the mean is the same as the degrees of freedom, and the mode is always 2 less than the degrees of freedom. So there's always a distance of 2 between the mode and the mean. And the mean is the degrees of freedom. The median is always somewhere between those two values. So I have vertical lines drawn here. By the way, to draw a vertical line on your calculator, there's a vertical command, and you just, from the home screen, vertical 20 means draw a vertical line at 20. Vertical 18 draws a vertical line there, and vertical 19 point, I typed all these numbers in. Enter, and these 3 vertical lines are here. So the one at the, you can tell the mode, it's the one at the maximum, right there at the top. So that's the lowest line. 2 to the right of that is the one that's at the degrees of freedom, 20. That's the mean, that's the one on the right, and the median is between those. This is a typical kind of pattern of going mode to median to mean. This is a typical kind of pattern when you have a skewed to the right graph. It's kind of cool that it turns out that it's such a simple formula when it's all said and done for the mean of the distribution, and it's the same as the degrees of freedom. Kind of cool. And the mode being just 2 less than that, that's also kind of a neat little result. The median's always between the two. Like I said, I've written out a proof of that, but it requires calculus, so we're not going to go over the proof. Alright, so let's look at some exercises as how we can use these techniques. So suppose we're taking samples of size 20 from a population where the standard deviation of the population is 5. And we do a sample is 5.7, compute the chi-square statistic. We want to be able to graph the PDF of the chi-square statistics if this process is repeated, and graph the CDF. So in other words, graph a PDF and a CDF when you have a sample size 20. Use the PDF and CDF to compute and illustrate the probability of chi-square less than 3, probability of chi-square is greater than 12, and of course we have to do this with only with the CDF only, but use it to compute some inverse probabilities. The first one is a right tail probability is 0.05. What's the critical value? What's the boundary value there of that right tailed area? And then the last one is a left tailed area. So let's take these one at a time, all related to this same situation where we're taking samples of size 20. Population standard deviation is 5. So let's find this chi-squared test statistic. Remember, the chi-square statistic is n minus 1 times s squared over sigma squared. Well, we've got all these numbers, so we'll plug them in. 20 minus 1 is 19, so that's 19 degrees of freedom. I can do 20 minus 1 in my head, so that's 19 here. S is 5.7, and sigma is 5. So here it is on the calculator, parentheses, 19 times 5.7 squared, close parentheses, divided by 5 squared, and I get 24.6924. And so that is our chi-square statistic. So we've sort of standardized it in a way. Not the same way as a z-score, but a similar idea. Alright, now let's try the next part. Suppose that we're taking samples of size 20 from a population where the population standard deviation is 5, and graph the PDF for the distribution of chi-squared statistics. If we were to do this over and over and over and over again, each time we would get a different chi-square value. What would the distribution of those chi-square values look like? Okay, you should be able to do this now, so press pause and come back when you get it done. Okay, well now that you've done this, you should have done this. We're doing a chi-square PDF, so you choose, you go to y equals, put it in, say, y1 or whatever, whichever one you want. Let's say y1. And we go to distribution, which is second variables, second VARS. That's distribution. Choose chi-square PDF. It'll be down probably the last one on the first page there. And then we give it x, comma, and then the degrees of freedom, which are 19. Choose an appropriate window. 19 is still pretty close to 20. 2.5 times that would be 50. It's close. 50 is okay. So about 50. And then you have to experiment a little bit with it to see how tall to make it. I ultimately settled in, after a little bit of trial and error, on negative 0.03 to about 0.1. And that's this picture. When it graphs, that's decent. There are some slightly different choices you could make for the window, but you can see it's starting at 0 here, kind of goes up, looks a little bit like a normal curve, but it's skewed to the right. Alright, suppose we're taking samples of size 20 and we want to graph the CDF. By the way, look at the last one. Notice that the population standard deviation didn't come into it. Just like if you wanted to graph a normal distribution, a standard normal doesn't depend on, well, standard normal is a standard normal. It doesn't matter what the population standard deviation and mean were. What you do is you take your sample mean minus the population mean divided by sigma. That standardizes it, so it's bound always to the standard normal, and we could use that. In a similar way, we're standardizing here. So, also, it's a little more like the t-distribution, however, because the t-distribution you also needed to know a degrees of freedom. So really, the only thing that comes into play in the t-distribution is how many degrees of freedom. Same way here, the chi-square distribution that you graph only depends on the number of degrees of freedom. So here, this population standard deviation is 5. That doesn't have anything to do with the way the graph's going to be. So we want to graph the CDF. Go ahead, you can do this now. Press pause. Okay, hopefully you're back and you've done this one. So now instead of a chi-square PDF, I turned that one off, and I'm graphing the chi-square CDF. This is ran off the screen here after I got to the end, but it should say chi-square CDF. And of course you get that again from distribution, which is second variables to get distribution. And it's the first, you have to go down because it's not listed on the front page. If you keep going the down arrow, you'll run into it as the first one on the next page. Or if you know its number, you can just type it in. Like if it's number 8, maybe it's number 8, I forgot. You just type in that number 8 and it'll go right to it. Basically, I could leave my x's like I had them before, but I want to change my y's to my standard one I use from negative 0.3 to 1.1. It's kind of a good standard window for CDFs. And of course, if it's a CDF, you should see that it starts at 0 on the left and ends at 1 on the right. In this particular case, it actually is going through the origin, or starts at the origin, kind of comes up, increasing, concave up, somewhere it hits an inflection point, and then starts increasing but concave down, levels off but never actually reaches y equals 1, which is our asymptote on the right. Basically, it's going from 0 on the left to 1 on the right. Now, let's take, again, take samples of size 20, and how can we compute the probability that chi-square statistic is less than 3 when you have 20 sample size, so that's 19 degrees of freedom, and illustrate this on both the PDF and CDF. You should be able to compute these on the CDF and PDF right now. Go ahead and compute those and then come back. Press pause now. Well, on the CDF, if the CDF is graphed, all I have to do is just do trace. So I can do, since this is a left-tailed probability, a cumulative probability that chi-square is less than as number 3 in this case, just do trace 3. And of course the y value here is that probability. Remember, this e negative 5 is times 10 to the negative 5th, So power. So that is a scientific notation. So you move the decimal 5 places to the left. So that's actually 0.4 zeros, then to 1079. So it's a very small probability. If we've got the graph of the, so that was the graph of the CDF. If we got the graph of the PDF over here, then we can do it from the graph by doing our shading. That's second calc, and I believe it's number 7, which is our area calculator. And it's going to ask us for a lower bound, which is 0, an upper bound, which is 3, and it's going to shade from 0 to 3. And it's really hard to see it here, but it's actually shaded. 3's right into here. If you can see where my cursor's moving around, it's going from 0 to 3. So there's some shading there. It's hard to see, and that area is very small. Very, very small. Now, if you don't want to draw the pictures, if it didn't say anything about illustrating, we could just compute that. One way we can do is compute it with an integral or function integrate from the PDF. So we integrate from 0 to 3 PDF of x, comma 19 dx, same number. But I think the easiest way to do this one, if all we need to know is this probability, the easiest way is the top one on this screen right here. Just do a chi-square CDF, say go from 0 to 3 with 19 degrees of freedom, boom, hit enter, you got it, there's your probability. You don't have to go through the graph of anything to do that. But you can illustrate that areas are probabilities under the PDF, or they are y values on the CDF, specifically cumulative probabilities. Alright, what about this one? Find the probability that x squared is greater than 12. See if you can figure this one out. Press pause now. Okay, going on. Again, the easiest way to do this one, well, we could either go chi-square CDF, go from 12 and put some big number on the right that's like infinity. But we got a really nice, neat edge on the left side of 0. So I'm going to do the complementary probability and then subtract from 1. So I'm going to do 1 minus the probability that chi-square is less than 12, which is just a chi-square CDF from 0 to 12. Again, with 19 degrees of freedom. So 1 minus chi-square, 0, 12, 19, turns out to be 0.88, 5, 6, etc. in the screens you see, screenshot from the upper right. Now, if you want to do it on the picture, okay, we can use the PDF, and I can also illustrate that with the CDF. So what we want to do here is, on the CDF, we would find 12, and we would integrate to infinity, or in this case, just to the edge of the screen, which is as far as you can go. And that shaded area, the probability is not showing up at the bottom, but that shaded area is this 0.885. Now we can also find the y value that goes with the CDF. However, if I do it at 12, the y value I get is 0.11437, etc. Well, so if I go quit and type y and enter, that is the y value that I get. What I want is 1 minus that y, which is 0.88, because the y value here on this curve is the area to the left. So the unshaded area down here is the 0.11. So the shaded area to the right is what we're looking for, which is the 0.885. How are we going to do this problem? This time we're given not the x value or chi-square value, but we're given the probability, and we want to find the x value of the boundary of that region that's going to have that probability. Well, this is an inverse chi-square. Again, remember that there's not an inverse chi-square built into the calculator like there is for an inverse normal or inverse t, but that's no problem for us. If we've got a CDF, we're good to go on inverses because we know how to do this. You should know how to do this problem. Go ahead and do this one now. Press pause. Okay, well, we're back here, and of course the way to do this one is to graph the chi-square CDF and then the cumulative probability, which is 0.05. Remember, this is a left-tailed kind of a probability, and so or a cumulative probability that chi-square or x is less than that c. That's exactly the kind of thing that gives us a y value on a CDF curve. So if I just graph that y value of 0.05, I'll get a horizontal line there, find where that crosses the CDF. So by doing a calc intersection, and of course y is 0.05, but then the x is the x value we're looking for, 10.117013. Let's try another one. This time we want essentially a right-tailed area. Probability that x squared is greater than c. Of course, when I refer to that to the area, I'm talking about or thinking about the PDF curve. What we really want to think about is just the y values on the CDF curve. See if you can do this one now. Press pause. Okay, now that you're back, we got to be a little careful on this one because remember the CDF always gives us probabilities that to the left probabilities, cumulative probabilities. So it doesn't do to give us something like probability of chi-square is greater than c. We need chi-square less than c. Well, the probability of chi-square less than c is 1 minus this probability that it's greater than c. So that's going to be 0.05. So the probability that chi-square is less than c is 0.95. 1 minus 0.05 is 0.95. So now this is the kind of expression that we were dealing with them last time, and we can make this work for us. Again, graph that chi-square CDF, same one as before. This time I want to graph the horizontal line at 0.95 and calculate the intersection there, and you see it's about 30.1. Now I could go back and double check and verify these things by looking at shading in the PDF, but honestly there's no need to that. In fact, just like with the normal and the t-distribution, you really shouldn't have to use the normal PDF and t-PDF or chi-square PDF unless you strictly want to graph that and look at it. I think it's useful to think about the PDF and see it, so some of these pictures are very useful. But in terms of actually doing computations, all you need is the chi-square CDF to compute probabilities, and then, well, you're going to have to graph horizontal lines and do intersections with the chi-square CDF to find inverse probabilities. Alright, let's look at another exercise. This time we're taking samples of size 30 from a normally distributed population. And by the way, remember that normality requirement on our individual data that we're drawing from is very important. In fact, the chi-square distribution is more sensitive to that. Oftentimes, even if you don't have a normal distribution and you're doing, say, a t-test or a z-test, they're pretty good. They give you something that's at least useful and it's kind of close. But if the normality requirement is not there on the chi-square, it can be very sensitive to that, particularly to distributions that are skewed a bit on the underlying distribution. So that can really throw these values off so much that this really just doesn't work. So that's a harder requirement than it is for the other one. In other words, it's a more important requirement. So let's try this here. We want to use the CDF to compute the chi-square critical values such that we'll call this one on the left critical value a chi-square value, chi-square sub L, the lower limit, and to the left of the lower limit the probability is 0.05, and then we also want a corresponding one on the right so that the probability above that is 0.05. Now, unlike the normal or t-distributions, standard normal or t-distributions, we don't have 0 in the middle and this thing's symmetric. In fact, this graph's not really symmetric about any way. It's skewed to the right. So we can't just, for example, find the lower and then take the opposite sign for the upper like we could in say, the standard normal or t-distribution. A little bit more complicated, but we can still compute these values. These are just inverse norm values, inverse chi-square values, and we've just been talking about how to do that with the calc intersect. And now, once we found that, that means that the area between those two is 0.9. So that's sort of a 90% area in the middle, half a percent, 90% in the middle, 5% on both ends. So a total on both tails of 10%. And actually, we're going to shade in this graph of this 90% in the middle on a PDF. So let's see if you can do that now. Press pause. Come back when you get it done. Okay, so let's take a look at this. Okay, so I want to use this chi-square CDF really to basically compute everything. So the chi-square CDF, again, 0, x, 29, because this population size is 30. And I'm going to need horizontal lines at 0.05 and 0.95. And you can kind of see it on the picture. Between these two places where it crosses is my area, my region, where I'm going to have a probability of 0.9. And to the right of this intersection, the top intersection, and this intersection down here on the bottom, to the left of that, each of those areas is 0.05. Okay, so just do a calc intersect. I've got three things going here, so I need to be really careful which ones I select. But as long as I select the CDF and the y equals 0.05 curve, I get the right intersection there, which is about 17.7. And then calc intersect again. This time choose the CDF, then this top line at 0.95, and we get what we're after. Now, by the way, look at the one on the left one. Notice I just used 0.05 because this is a chi-square less than some value we're looking for. But if I have a chi-square greater than, then I need to look at the complementary probability. So this says the area is 0.05 to the right, or probability is 0.05 to the right. That's an area when we're talking about here. When we're talking about the PDF, which you see here, it's a y value here. So the difference between this one and 1 is the 0.05, but its actual distance from 0 is 0.95. So we got to use 0.95 for that. Okay, and calculate those things, and we get 42.56. And so those are the two lower and upper values. I actually stored them as L and U. Now, to get this shaded thing here, I regraphed it, and this time I got rid of my 0.05, I got rid of my 0.095, I turned off my chi-square CDF, but turned on my chi-square PDF, x, 29 again, 29 degrees of freedom. And this time I did the area shader, calc, second trace, which is calc, and choose, I believe it's number 7, and it said lower limit, and I just typed in alpha L because I already saved this, or I could type in all these numbers here. And then when it says for upper bound, I typed alpha U because I'd already had it saved, stored as U, or just type in all these numbers. And it shades that area in between. And this is our 90% right here, with our 10% being split evenly between the two unshaded areas. So the unshaded area on the left is 0.05, and the unshaded area to the right is 0.05. Notice how this is not symmetric about either it's definitely not symmetric about the mode there. Now, if you look at this, we have all the pieces we really need to do to set up a confidence interval. So let's work with this and see if we can come up with a formula that's going to allow us to find a confidence interval. Now, I want to just show you one little algebra thing, or arithmetic or algebra thing here. If we're dealing with positive numbers a and b, then you have 1 over a is less than b, then multiply both sides by a, that's 1 is less than a times b. Then divide both sides by b, it's 1 over b is less than a, which is the same thing as saying a is greater than 1 over b. So notice if I start with the original, 1 over a is less than b, and reciprocal both sides, I get a on the left and 1 over b on the right, but look what happens. It switches from a less than to a greater than. So in general, if you reciprocal both sides of an inequality, you can do that, but it reverses the direction of the inequality. Okay? Now, what we're looking for with a confidence interval, basically, at least to begin with, we want to find an interval where chi-square value is somewhere between a lower and an upper limit. Okay, so the chi-square is going to lower is going to be an inverse chi-square, where you have alpha over 2 to the left, and of course you have to give it whatever degrees of freedom you have, and the upper limit is a chi-square. You have 1 minus alpha over 2 to the left because you have alpha over 2 to the right, and then you give it, of course, the degrees of freedom. Of course, unfortunately, we don't have this command, inverse chi-square, in our calculator, but we know the process by which we can find that. Okay, so let's just keep running with this a minute. So we have the chi-squares between chi-square lower and chi-square upper. Those are our boundary points. So if you think back of the visual, let's just look back. So if you're looking here on the PDF, we're trying to find this critical region there is kind of the shaded region. And so this case alpha is 10%. So you got 5% on the right, 5% on the left, 90% in the middle. So this would be like for a 90% confidence interval. And we want to find these lower and upper. The chi-square lower is this place on the left, and chi-square upper is this place on the right for the boundary of that region. That's basically what we're looking for. Okay, now let's look at that. Now remember, chi-square is n minus 1 times s squared over sigma square. Okay? Now, what I want to do is I want to solve this for, ultimately, to get sigma square in the middle. Because what we want to do is we want to find an interval for, a confidence interval for sigma square. Not really for chi-square, but for sigma square. Okay, so the way we're going to do that is we're just going to do a little algebra here. So the first thing I did is reciprocal everything. So that I get 1 over chi-square left, lower on the right, left. On the right I get 1 over chi-square upper. On the middle it flips over, so I got sigma square over n minus 1 times s squared. Now, when I reciprocal everything, as we just saw, we have to reverse the inequality. So now, instead of 2 less thans, I've got 2 greater thans. Now I'm going to multiply everything by n minus 1 and s squared, and notice that n minus 1 and s squared are both positive numbers. So notice, by the way, also we need a sample size of at least 2 for this to work. Okay? In fact, we're probably going to use this on sample sizes of 3 or more. But anyway, we multiply by n minus 1 times s squared, multiply all 3 sides by that. And so we get n minus 1 s squared over chi-square lower is greater than sigma squared, which is greater than n minus 1 s squared over chi-square upper. And now I'm going to just rewrite that in our normal way from left to right, so that the least number's on the left and the greatest number's on the right. And so this gives us our interval n minus 1 s squared over chi-square upper less than sigma squared, which is in turn less than n minus 1 times s squared over chi-square lower. And one thing that's a little tricky about this, not necessarily that tricky, is this reciprocal thing, reversing the inequalities, gave us something that's interesting, that the chi-square upper from the basic picture is actually used to find the lower side of our confidence interval, and the chi-square lower is used to find the upper side. Okay, but anyway, we have now basically a formula for finding our confidence interval for sigma square, for the variance. Chi-square lower, sub L, is our inverse chi-square of alpha over 2, and of course you give it the degrees of freedom. Chi-square upper is the inverse chi-square of 1 minus alpha over 2, and give it the degrees of freedom. Again, unfortunately, these inverse chi-squares are not built in the calculator, but we know how to do it. We just graph y equals alpha over 2, graph the chi-square, CDF, do a calc intersect, we've got chi-square lower. Graph 1 minus alpha over 2, that'll be a horizontal line up the top. Graph the chi-square, CDF, calculate intersection, and now we've got chi-square upper. And of course, sigma is an element of this here, n minus 1 times s squared over chi-square upper, comma, n minus 1 s squared over chi-square lower. And we can take the square root of everything to find an interval for sigma. The square root of s squared is s, and then you've got the square root of n minus 1 over chi-square upper, and again this s is out here, and square root of n minus 1 over chi-square lower. Now, when I say sigma square is in there, the variance is in this interval, or the standard deviation is in this interval. That's where we hope it's going to happen, and approximately 1 minus alpha, whatever that percentage is of the time, that's what's going to happen if you do this process over and over and over and over and over again. Once again, as with any confidence interval, remember that it's not the sigma square that's moving around. The sigma square is there. This population has some variance. We just don't know what it is. But we can do a sample, and we can estimate that variance. Of course, the point estimator, best point estimator we have for the variance is the sample variance. That's the best estimator of the population variance. Okay? But it's better to estimate with a confidence interval than with a single point. And of course, we can use this formula. So there's pretty straightforward formula there for us to use. Notice, however, it's a little different kind of formula than we had for means, because the mean was always, the sample mean was always right smack dab in the middle of this interval. The sample variance is not necessarily right smack dab in the middle. This is not sample variance plus and minus something to find the limit, the things. It's sample variance times something on the lower and upper. So that's going to give us a little bit of different type of an interval. Okay, but sigma square is, but s square is somewhere towards the middle of this region, and sigma square we hope is in that. And we're sure, how sure? Well, 1 minus alpha that gives the level. So let's put this to work in an example. Okay, let's go back. You might want to jot this formula down. So jot that formula down. Okay. And then let's try this next one. A company is manufacturing something, a part, and is measuring the diameter. Suppose the diameters of the individual parts are distributed normally. Again, that normality assumption is important, or this test just does not work. They take a sample of 20 parts and compute the standard deviation of the diameters of the parts to be 0.02 centimeters. Compute a 95% confidence interval for the population standard deviation of the diameter of these parts. The sample standard deviation was 0.02, so that's our point estimator. Let's make a confidence interval estimate of that same statistic. You should be able to have all the tools you need to do this one. So let's press pause here and then come back when you've got it work. Press pause now. Okay, so notice that n is 20 means the degrees of freedom is n minus 1, which is 19. Now that should be a lowercase in there. And a lowercase s is 0.02. The confidence level is 95%, or 0.95, so the remaining 5% is split equally, half below and half below the lower limit and half above the upper limit. So that's 0.05 to the left, 0.05 total, split in half is 0.025 to the left, 0.025 to the right, the 0.95 in the middle. So the left of the lower is 0.025, the left of the upper is 0.975, 1 minus alpha over 2. So in other words, alpha over 2 is 0.025, alpha is 0.05, and then 1 minus alpha over 2 is 0.975. So the U and the L are the chi-square lower, chi-square upper, not the lower and upper confidence of our confidence interval. Okay? Use these levels to compute the critical chi-square levels where the degrees of freedom is, of course, 19. So we're going to use our calculator to compute these critical values L and U. That's chi-square lower, chi-square upper. And again, we graph a chi-square CDF. Always goes chi-square CDF, 0x. The last number here is degrees of freedom, which is 19 in this case. We graph our two y values, alpha over 2, which is 0.025, 1 minus alpha over 2, which is 0.975. And it's between these two x values where they intersect is going to be our, well, not exactly our confidence interval. that essentially would be our confidence interval for chi-squares, but we want our confidence interval for sigma instead. So calculate those two intersections one at a time. We get a lower value of 8.9065165. When we're done with that, the first thing I would do at this point is quit. So second mode is quit. Type X store alpha L, and that stores that as L, so I don't have to type those values in again. Okay, actually it even gave me a couple more digits than it showed on the other screen. Then I calculated my other one, again quit, and stored that as U for upper. So that's chi-square lower and chi-square upper. Those are critical values there that we need. Now to find that, so those were my inverse chi-squares to give me these two numbers right here, and we're finding an interval for the standard deviation rather than the variance. So it's our sample standard deviation, 0.02. It's times a square root of n minus 1 over chi-square upper, and the standard deviation times n minus 1, the square root of n minus 1 over chi-square lower. Again, the chi-square lower goes for the right end, the chi-square upper goes for the left end, and so these numbers, when they get done, should be the lower number on the left and the higher number on the right. And there it is, rounded off to be approximately 0.015 to 0.029. And so notice that our sample standard deviation of 0.02 is in that interval somewhere, although not necessarily exactly right, not just the average of the two ends. Okay? Let's see if we average the two ends. Let's see if we add these up. That would be 0.044 divided by 2, 0.022. See, and that's not exactly where 0.02 is. It's a little bit different. And that's because that chi-square distribution is not a symmetric distribution. But anyway, there's how we find a confidence interval. Pretty straightforward. Unfortunately, this one's not built in the calculator, so we can't just do just a built-in shortcut. But the basic concepts are based on things that we already have worked with, and the fact that it's got the chi-square CDF in particular built in the calculator, that allows us really to find chi-square values, find the property of the if we're given a chi-square value, an x value, we can find a y, which is a probability, and by doing a graph and a horizontal line and calc intersect, if we're given a probability, we can find a chi-square value or an inverse chi-square. All right, let's try another exercise. This time I'm going to give you some data. A weight loss program results in the following amounts of changes in the weight of a sample of participants. All measurements are in pounds. So the first one is positive 1. That means he gained a pound. So the diet didn't really work for him. The rest of them were negative, so they all lost weight. One lost 2 pounds, a couple of them lost 3 pounds, and so forth. One guy lost 20 pounds. Okay? So here are the questions. What is our point estimator for the standard deviation of changes in weights? Use the method of the previous slides to find a 90% confidence interval for the population standard deviation and weight loss. And what assumption is needed for this confidence interval to be valid? And do you think this is a reasonable assumption in this case? So right now we're going to make the assumption needed to do this the way that we've done before, but then we also really need to think about if this is appropriate or not. So see if you can go ahead and do this. Let's start with the point estimator. Press pause now and come up with that. Well, the point estimator is just our sample standard deviation. Now remember, we know how to do this in the calculator. We go to list 1, clear it out, type all our data in. There's the first part of the list, but I've typed the whole list in. And then I do one variable statistics for list 1, which we've done this many times. So quit, go to the home screen, do stat, calc, one variable statistics, list 1, and you get this thing right here, x bar. So on average they lost about 7.6 pounds. But the thing we're looking for is S sub x, not sigma, because this is a sample. S sub x is 5.7109003024, and so that about 5.71 is our standard deviation. Okay, so that's our best estimate. Also, it counted them for us. There are 18 things here, 18 data points Find the confidence interval now using this information. Go ahead and do this now. Press pause. Okay. As we go on, notice the degrees of freedom are 18. We have S. We are looking at a chi-square distribution, so we need to find our critical values on the chi-square first. Graph it first. Graph the CDF. That's just what we need. 0 to x. That third number should be degrees of freedom, so it's 18. We graph our, well, let's see. Let's think about it a minute. It's 90% is our confidence level. That's 1 minus alpha, so that must mean alpha is the remaining 10%, or 0.1. We want to break that into half on each end. So the left half should be 5%, or 0.05. So it's always alpha over 2 there. 1 minus alpha over 2 is 0.95. These two numbers should add up to 1. And so that leaves 5% on the right. So this gives me my two horizontal lines along with my CDF. May have to experiment with my window a little bit. Let's think about this a minute. 18 is the degrees of freedom. We know the mean is 18. The mode and median are a little less than that. The mode's actually at 16. The median is somewhere between those two. And we can start at 0. And if you go out about 2.5 standard deviations, 2 times 18 is 36, and add another half of 18 and 9 to that. That's going to be about 45. So about 0 to 45. I may be still at 0 to 50 here. I don't know. But something like that should happen. So if we graph this, we should see it starting at 0 and going up to 1. It should already be leveling out pretty well there. And for this, it's a CDF, so I'm going to start at my standard negative 0.03 to 1.1. Works pretty well. That's probably the window I have. Then I did a calc intersect twice to find these. As I did each of these, I went ahead and stored them. By the way, I've done my statistical calculations. If I don't do any more statistical calculations, then these variables stay the same. So notice down here on the screen on the lower left, I have S sub x. So to get that, I pressed variables, chose, I think it's number 5, statistics, and you'll see S sub x there, and you can pull that up. You can also pull up x bar and en and whatever from our data set that we just did. Or I can just write it down and type all those numbers if that's easier, whichever is easier for you. Now, as I calculated these things, I'm lazy enough. I don't want to type all these numbers, so I'm gonna store these things. So I'll calculate that one there, and then get to the home screen and store x and L. Then did the second one and calculated it and stored x as u. So now I have S sub x, L, and u, and that's exactly all I need to find my confidence interval, because the lower part of the confidence interval is S sub x times the square root of the degrees of freedom, 18, divided by u, the upper thing from our inverse chi-square, the 28 point whatever. Plug that in there and I get about 4.509, and do the same. Then I just did second enter and got the same thing back and replace u with L, and now I get the 7.907. So we're 90% confident that if we were to do this process over and over and over and over and over again, 90% of the time, that would capture the true standard deviation. So we are 90% sure that the true standard deviation is in this particular interval. Again, one more time. As with confidence intervals, as with any confidence interval, the true population parameter, in this case the standard deviation, is not moving. It is the confidence intervals that are moving around. But it is correct to say that 95% of the time, as they move around, 90% of them in this case, will contain the true population standard deviation. Now, remember what assumption is needed. Well, for this to be true, the underlying individual data must come from a normally distributed population, and it is pretty sensitive to that, much more so than, say a t-distribution or z-distribution, z-test, or t-test, or z-interval, t-interval. Well, I just did take the data and did a dot plot. The good news is you do see kind of some concentration in the middle and somewhat symmetric here, but it looks more uniform almost than it does normal. So a little bit of a question mark there. This doesn't have a really good looking normal shape, so I'm not really sure if that's a good assumption in this particular case or not. We're not going to cover this in this class at this point, but there actually are a bunch of normality tests to take the data and test it to see if it is normal. And there are some tests for measuring some of these things, doing confidence intervals and hypothesis testing, that doesn't depend on knowing that it's normal, but those are different kinds of tests, not the kind that we're studying here. Well, I mentioned a test. Let's do one. Let's do a chi-squared test to test a variance from one sample. Now, this particular kind of test is not built into the calculator. What we're doing here is we're taking a sample, finding our sample standard deviation, and we're comparing that to a hypothesized standard deviation from a population, or equivalently do the same thing for variances. Find the variance of our sample and test that against a known population or hypothesized population variance. There is another type of chi-squared test that's covered in a later section in your text, and this is the chi-squared test that's built into your calculator. So we won't be using the chi-squared test that's built in the calculator for this chi-squared test. But we have all the pieces, once again, to build a method for doing a test. Can't emphasize this enough. Recall that we must know that the distribution of individual measurements is normal for this test to work. So our null hypothesis is that the population variance is equal to some known or assumed population variance, and as usual we can have a left-tailed, right-tailed, or two-tailed alternative hypothesis. And as usual there is a classical and a p-value approach. So let's take an example. Suppose we have a manufacturer who claims that the variance of the mass of a part it's manufacturing is 3.4 grams. We want to test this claim, so we take a sample of 30 items and compute their masses. We first convince ourselves that it's reasonable to assume that the distribution of masses is approximated very well by a normal distribution. We measure the sample variance of the parts in this sample and find that that sample variance is 4.2 grams. At a confidence level of 95%, is there sufficient evidence to say that the true variance is different from 3.4 grams? Okay. Identify the null hypothesis, the alternative hypothesis, the test statistic, the p-value, the alpha level, and so forth, and the critical values. So we'll do it with both the classical and the p-value approach. Compare those. Okay, let's take a look at this. So our null hypothesis is that the true sigma square is our sigma square naught, our hypothesized value of 3.4 grams, what they claim it is. So, they said it's that. We're going to assume that they're not lying to us unless we have enough evidence to show otherwise. So that's the status quo. The last sentence tells us left-tailed, right-tailed, or double-tailed, two-tailed. And if you notice it says, at the confidence level 95%, is there sufficient evidence to say that the true variance is different from? That's just not equal. Okay, so that's two-tailed. So alternative hypothesis is not equal to. N is 30, so that means our degree of freedom is one less than that, 29. And our sample standard deviation, sample variance is 4.2. Now be careful with this, that you be sure that we, if we're talking about standard deviations, what you really need to do is convert them to variances, because this test really is for variances, because the chi-square distribution is dealing with variances, or it's based on variances. but it's still really the same idea. Just square them and go forward from there. Alright, so let's look at the p-value approach first. And all the computations are done that you need to do are just seen in this calculator screenshot up here on the right. So the first part's what we had before. We need to find our test statistic. So we need to do that first. And so that's n minus 1 s squared over sigma squared. And that sigma squared is our hypothesized sigma squared, which is 3.4. S squared was given to be 4.2. And there are 29 degrees of freedom. So all we need to do is 29 times 4.2 divided by 3.4. You can see that on the calculator. That's 35.82352941, about 36. Now we want to find the p-value that goes with that. Now notice that the 35 point whatever is already above the, well, just do it this way. The s squared, 4.2, is above the 3.4. So we're to the right of the hypothesized thing. So we're going to find the area that you're further out. That's even further to the right for the test than the test statistic is. Now remember, this is a two-tailed area. So if you're thinking about the picture on the PDF, you're going to have an area shaded to the right and an area shaded to the left, and those two areas are going to add up to p, and they're going to be the same area. So each area is p over 2. So the p-value is going to be twice the area on the right. So we can compute the area on the right. That's the probability that x squared is greater than 35.8235, etc. And so that'll be 1 minus the CDF from 0 up to there with 29 degrees of freedom, and twice that will give us alpha. So anyway, we compute that, and you can see that all I had to type in here was, look at the calculator screen up at the right, 2 times, parentheses, 1 minus chi-square CDF. One more time, that's from distribution, which is second variables, choose number, I think it's 8, and then give it 0, and then instead of typing all those numbers in, I just said second and answer, comma 29, which is degrees of freedom, close, close, and enter, and we get our p-value of 0.35752434747. In other words, a p-value of approximately 0.36. 0.36 is greater than our alpha level of 0.1, because I think we were going to talk about a 90% confidence interval, so that makes alpha 0.1. And so we do not reject. Remember, p is greater than alpha, do not reject. P less than alpha, we do reject. And I'll illustrate this in a minute, but notice this is probably the easiest way to actually do this test. And we really only had to do 2 computations, and they're not too difficult here. The first one is we computed the test statistic, which is used the formula n minus 1 times s squared over sigma squared. Straightforward there. 29 times 4.2 divided by 3.4. And then, since it was a right-tailed, since the number is to the right, the sample standard deviation is to the right of the hypothesized one, we find the area to the right there, that probability. But remember, we got to double that because that's because it's two-tailed test. If this had been a right-tailed test, we wouldn't have had the 2 times. Okay. However, the CDF. So there's really 2 ways you could do this. You could actually just do chi-square CDF from that 35.8 whatever to infinity, and then do 29. Put in something really big, like 1,000 or something for infinity, and you could have done it that way. It would have worked. Still would have had a double. Or we can do the 1 minus and go from 0 up to the 35 point whatever. So we get 0.36 for the p-value. That's the p-value approach. The classical approach is a little harder because you actually have to compute inverse chi-square values to find our critical values, particularly the one on the right. So notice that alpha over 2 is 0.025, 1 minus alpha over 2 is 0.975. We want to graph those 2 things along with the chi-square CDF with 29 degrees of freedom. And we see the 2 pictures here, at the bottom, and there's a window for you, and we do a calc intersection to find those critical values, which I rounded off to about 16.05 and 45.72, and the test statistic is between the two, 35.8, which we still have to figure out the test statistic, which I've already done, 35. So you got to do that no matter what. So over here, if the p-value approach, once I found my test statistic, I just find the area of alpha that corresponds with that, and then compare that directly to the area p, I should say, that corresponds to that, and then compare that to alpha. A little bit harder over here. Once I have my alpha level, I can compute my critical values. I never have to compute a p-value here, but I just compare my test statistic with that. Either way, you got to compute the test statistic. But the rest of the computations are here, but it does involve me doing this stuff here. So it's a little harder way to do it, but of course you get the same conclusion. We're in that non-rejection region. The rejection region is to the right of 45.72 and to the left of 16.05, and so that's our, since it's a two-tailed test, that's a two-tailed region, and we look at that. Now if I want to illustrate these, something not necessary, by the way, so if I were to actually do this problem, let's see here, back up, here we go. If I were to actually do this problem, I would have done this screen right here. I would have just, the only thing I would have ever had to type in is just exactly what's on this screen up in the upper right here. I wouldn't do the rest. I wouldn't do the critical value. I wouldn't do the classical approach. But, you know, if a question asked you that, you could do it. And if I needed to illustrate it, I know how to do that. This is partially illustrated here, at least. So again, here's all of our information that we just computed. And this time I'm going to change to a slightly different window, zoom in a bit on the up and down part, and I'm going to graph the chi-square PDF, and then first of all I'm going to shade some areas, so I'm going to use that several steps you don't see here, but I'm using the area calculator. That's the second trace, which is calc, and then choose number 7. And this first one, I did it twice without erasing my shading, and so the shading on the left, that should be an area of alpha over 2, and then the alpha over 2 on the right. So the total area in the first picture on the top here is alpha. The unshaded region is our confidence level 1 minus alpha, which is, so 90% is unshaded, 10% split into two 5% areas is shaded there. And so the boundaries of this are the L and the U, the 16.05 and the 45.72 that we found earlier. Then you draw I just drew a vertical line here at my test statistic, and of course it's clearly in the no rejection region. Okay, the non-rejection region. So it's not in the critical area, so you leave it alone. So notice this is the again, this is the classical approach. The p-value approach, we find our test statistic, and notice I've drawn a vertical line there, the same place, the same graph, same scale, so you can compare. And then I did the area from there on out to the right, because this is the right tail. This is the right tail. That area is p over 2. If I really wanted to complete it, I would find an inverse. Complete the picture, I could do some kind of inverse thing here and find an x value that gave me an area to the left of p over 2, so the total area here would be p. But this is half of p, and this is half of a, so I can compare half of p to half of a, and of course it's bigger, so we don't reject. Alright, I think that gives us a pretty good look at using the chi-square distribution to give us hypothesis testing and confidence intervals for variances and essentially standard deviations as well. Again, this is what are our requirements. We must have a normal distribution of data to begin with of individuals, and we're testing a single sample against a known population for this type of chi-square test.